Picture a busy street for a second. You've got vehicles rushing by, pedestrians crossing at the lights, maybe some leaves blowing in the wind. At first glance, it just looks like everyday chaos. But beneath the surface, what you're really seeing is a beautifully complex story of change. And the amazing thing is, everything happening out there can be understood and predicted. How? By reading the physical world through the profound and honestly fascinating language of motion. Now, motion challenges some of our most basic assumptions. It isn't just movement. It's not just the simple act of things shuffling from one place to another. Fundamentally, motion is how we describe change in the physical world. And it's about doing so with incredible precision. It's a huge shift, really. We're moving from just casually noticing that something is moving to truly understanding what that movement actually means. So, what is it exactly? At its most basic, foundational level, motion simply means a change in an object's position over time. It sounds simple, right? But this concept is incredibly powerful. If something doesn't change its position, well, it's not in motion. But if it shifts, even by a microscopic amount, motion is happening. It's important to remember that motion isn't some hidden property stuffed inside an object. It's a dynamic relationship between the object itself, a specific place, and the passage of time. And this brings us to a primary rule of physics. Motion absolutely requires a reference point. Think about a passenger sitting inside a smoothly moving bus. To that passenger, the person sitting right next to them looks completely still, right? But to an observer standing outside on the sidewalk, both of those passengers are rushing past at highway speeds. It is the exact same object being observed, but we get two completely different descriptions. You see, an object isn't just moving or not moving in some absolute sense. It is always moving relative to something else. It's a lot like reading a map. A road isn't just north or south all by itself. It only gets that meaning from the map's orientation, usually a starting landmark or a compass rose. Well, motion works exactly the same way. Without a reference point, the whole concept of moving is pretty vague. But the moment you establish that reference point, answering the all-important question, compared to what, it instantly transforms into a precise scientific statement. What this means is that rest and motion aren't absolute, rigid opposites. They're simply different ways of describing a position over time, and it depends entirely on your chosen perspective. Let's say you're holding a cup of water while walking down the street. That cup is at rest relative to the hand holding it, but it is in continuous motion relative to the ground. Both of those statements are completely true at the exact same time. It's all about your frame of reference. Building on this, we have to talk about time, because time is an indispensable factor here. You see, an object's position only provides a single static snapshot. If a book is sitting on a table, its position is fixed at one single moment. But to actually capture motion, we have to compare a before and an after. The critical question becomes, does that position stay fixed across those moments, or does it shift as the clock ticks? Consider checking the water level in a large tank. If you look at it just once, you only learn how much water is there at that exact second. To know if water is actually flowing in or draining out, you have to look twice. Time has to pass to measure the flow. Motion works exactly like that. One look is literally never enough. Time is the essential ingredient that gives motion its actual meaning. Now, this is where our everyday intuition often clashes with physics. Imagine a person standing perfectly still, straining to hold up a massively heavy box. They might be sweating, their muscles might be shaking, they're putting in a huge amount of physical effort. But if their position isn't changing, from a physics standpoint, there is zero motion. Contrast that with a smooth stone rolling effortlessly down a hill. Motion is entirely about positional change. It has absolutely nothing to do with the amount of physical effort or how dramatic the event looks. It operates a lot like a piece on a chessboard. A specific move might be incredibly dramatic and absolutely crucial to winning the entire game. But what defines the piece's motion isn't its strategic importance or the tension in the room. Its motion is defined strictly by whether it physically changes squares from one turn to the next. That positional change is the only metric that matters. So understanding that motion is a change of position over time relative to a reference point allows us to ask some sharper questions, like what exactly changes when motion happens? During any physical journey, there is the actual ground you cover with your footsteps, and then there is your final resulting location compared to where you started. In our everyday conversations, we often blend these together, but in physics, they tell two very different stories. It is absolutely vital to separate how much ground was covered from how far the final position shifted. Distance is the total path taken. It faithfully counts every single twist, every turn, and every detour of a route. Displacement, on the other hand, measures only the straight line, net shift in position from the exact starting point to the finish line. Think about how a bank account works. Distance is kind of like the total amount of money moving in and out. Every small deposit you make and every single dollar you spend, all added up. It measures all the activity. Displacement is just the final net balance at the end of the month. Hundreds of dollars could flow in and out, but if your balance ends up exactly where it started, the net change is zero. It's just like walking for miles in a giant circle. You covered a massive distance, but your displacement is zero. So, what turns a plain measurement into a truly meaningful description? Direction. Direction acts just like an arrow, showing both the size of the movement and its orientation. Moving 10 meters to the right is simply not the same as moving 10 meters to the left. Once displacement enters the picture, direction becomes an unavoidable and essential part of the story. It literally turns a simple dot on a map into a deliberate journey. And this distinction applies directly to how quickly a position changes, too. Speed simply measures how fast something is moving. It cares only about the distance covered over time. Velocity, on the other hand, combines that speed with a specific direction. It's built from displacement and time. Two trains might share the exact same speed of 100 kilometers an hour, but if one travels north and the other travels south, they are describing entirely different motions. They have completely different velocities. When you look closely, these concepts organize themselves into distinct families. Distance and speed belong together. They completely ignore direction and care only about the total path length, or how fast an object moves. Displacement and velocity form a completely different family. They care deeply about the net shift and the specific direction, completely ignoring the winding path in between. When viewed this way, motion stops feeling like a random list of definitions you have to memorize and reveals itself as a highly cohesive, logical system. And weaving through all of these concepts is a hidden partner, time. Time does a lot more than just measure motion. Time gives motion its shape. Imagine a bus traveling between two distant cities. If you only know the total route length, you know almost nothing about the actual trip. But factoring in time, knowing the length of the pauses, whether it moves steadily or if it spent hours stopped in traffic, that reveals the true nature of the journey. Time transforms a blurry idea of moving into a sharp, crystal-clear picture of how it happened. A really helpful mental model for bringing this all together is a piece of a film strip. Think about it. A single, static frame represents position. The sequence of those frames playing out over time, that is motion. The winding path a character takes through the scene represents distance. Their final location when the director yells cut is displacement. The pace at which the scene plays out is speed, and the specific direction they move, right across the screen, is velocity. A single frame isn't a story until they all connect, layer by layer. Physics honestly only feels confusing when we mix these distinct questions together into one vague idea of moving. Are we asking about the long path taken or the straight line net shift? Is the question about how fast or in exactly what direction? Once you unpack those underlying questions and separate them out, the confusion completely fades away. All the guesswork is replaced with a precise, clear diagnosis of exactly what is happening. This brings us to a really profound realization. Motion is not just a lonely fact sitting by itself. It is a rich, dynamic relationship between an object, a reference point, a direction, and time. Seeing motion as this structured system of relationships, rather than just a collection of random formulas to memorize, is a total game changer. It allows us to read the physical world around us with absolute clarity and confidence. So, armed with this new language of change, the everyday world starts to look entirely different. The next time a car passes by, a bird flies overhead, or even just a leaf falls to the ground, take a second and ask yourself, what kind of change is truly occurring? What is the reference point? What is the displacement? Because by applying this lens, everyday chaos transforms into a predictable, beautifully structured story of motion.